So my name is Mark Bollinger, and I am with the Lawrence Berkeley National Laboratory, and I'm joined today by my colleague Deb Milstein, who is also with Berkeley Lab, and also Eric Lance, if we can figure out the technical difficulties that were preventing Eric from joining. He'll also be with us. He's with the National Renewable Energy Laboratory, and the three of us are going to walk you through some analysis of wind turbine scaling in the United States, looking at the impact of larger rotors in particular, but also taller towers on capacity factors, the levelized cost of energy, or LCOE, and also the wholesale market value of wind energy. Before we get going, there are just a few things that I want to note. First, if you have any questions during the presentation, go ahead and type them into the Q&A box at any time, and then we'll try to address those most likely at the end of the presentation. There is a chat box, but we'd prefer that you not use that you use the Q&A box instead. The webinar is being recorded and will be posted on our website in the near future. And finally, this work was funded by the U.S. Department of Energy's Wind Energy Technologies Office, and we appreciate their support. Okay, so here's how the presentation will flow. First, I'll start out by looking at historical trends in turbine scaling, particularly the increase in the swept area of the rotor relative to the capacity of the turbine, resulting in a reduction in what's known as the specific power rating of the turbine, and then the impact that that's had on both capacity factor and LCOE. And then I'll hand it off to Eric to run through some geospatial analysis that NREL has done to determine whether this trend toward lower specific power ratings is likely to continue going forward, at least from an LCOE perspective. And then next, because LCOE is only part of the story, Dev will examine the impact of lower specific power turbines on the wholesale market value of wind energy. And then I will quickly take it back and talk about a few tangential benefits of lower specific power turbines, namely reduced transmission costs, lower balancing costs, and improved financing terms. And then after all that, we should have some time left to answer your questions. So starting with historical trends, here we see data on wind turbine scaling in the US over the past decade. The graph on the left uses physical units, namely megawatts and meters, while the graph on the right shows the percentage change in these various parameters since 2009. The average tower height really hasn't increased all that much since 2009, growing by only 12%, while the average rotor diameter and nameplate capacity have both grown by about 40%. But what really matters more so than rotor diameter is the swept area of the rotor, which if you remember your pi r squared formula from high school geometry class, the swept area grows with the square of blade length. And as you can see in the right-hand graph here, the rotor swept area has essentially doubled over this period, greatly outpacing the 40% increase in nameplate capacity, leading to a 30% reduction in the specific power rating of the average turbine, as you can see down at the bottom in purple. Now, I've mentioned the term specific power several times without really defining it, so let me just take a minute to do that because it is an important concept to understand for the rest of the webinar. Simply put, specific power is a measure of a turbine's rated capacity relative to the swept area of its rotor, and it's expressed in watts per square meter. So if the swept area of the rotor grows by more than the rated capacity, which is what's been happening in the US and elsewhere in recent years, then your specific power will decline. So it's a little counterintuitive in the sense that a larger rotor leads to a lower specific power rating. Here on the next slide is perhaps a more visual representation of turbine scaling with the 2009 and 2018 average turbines drawn to scale. Again, the most notable difference between these two turbines is really the rotor swept area. Changes to tower height and nameplate capacity have both been rather modest, but the rotor has obviously grown quite a bit, essentially doubling in its area, leading to a reduction in average specific power from 329 watts per square meter in 2009 to 230 watts per square meter in 2018. And as a bit of a teaser, later in the presentation, we will analyze the effects of moving to the much larger, lower specific power turbine that's shown on the right, and we'll call that turbine the low SP turbine, which stands for low specific power. And you can see that that one has a rating of 150 watts per square meter, which is a level that's not really commercially available yet, at least not on a 5 megawatt turbine. I have heard of some 2 megawatt machines kind of built on a bit of a prototype basis in China that have approached the 150 watts per square meter level, but that target is obviously much more difficult to achieve for a larger capacity turbine because your blade needs to be that much longer. Which raises the point that there are obviously several different parameters changing among these 3 turbines, including tower height, capacity, rotor diameter, and hence also specific power. But on this next slide, I want to focus specifically on changes in the rotor and hence changes in specific power, since that's primarily where we focused our analysis. So here we're looking at a 5 megawatt turbine on a 140 meter tower in all 3 cases, while the 3 different rotors that you see there are scaled to correspond to the changes in specific power that we've seen between the 2009 and 2018 average turbines, as well as the low SP turbine that I mentioned. So for this hypothetical 5 megawatt machine, reducing specific power from the 2009 average of 329 watts per square meter to the 2018 average of 230 watts per square meter requires increasing the blade length by 20%. So moving from this smaller red rotor to the larger blue rotor. And again, due to the pi r squared formula, this 20% increase in blade length expands the swept area of the rotor by 44%. This 44% greater swept area in turn captures more of the energy in the wind passing by the turbine at any given moment, causing the generator to run closer to or at full capacity more often. And all else being equal, this will increase the turbine's capacity factor. And this is really the primary benefit of lower specific power, namely an increase in capacity factor. And as we'll see a little bit later, if you can achieve that higher capacity factor at a reasonable upfront cost for the longer blades that are required, then you'll also reduce your LCOE as well. Okay, so these 2 maps show where turbines with the lowest specific power ratings and tallest towers are located in the US as of the end of 2018. Low specific power turbines are often thought of as low wind speed turbines, but the map on the left shows that deployment of low specific power projects has really not been limited to low wind speed sites. In fact, most of these projects are in the very windy Midwest and Great Plains regions. The map on the right, meanwhile, shows that the tallest towers tend to be concentrated in the Great Lakes and Northeast regions, where wind shear is typically thought to be the greatest, which in turn makes it worthwhile to build higher. Earlier, I mentioned that all else being equal, a lower specific power leads to a higher capacity factor, and you can see that very clearly in the empirical data on this slide. So the graph on the top left groups about 63 gigawatts of wind into 5 different specific power bins across 4 different wind resource bins, and shows that you can get just as much of a boost in capacity factor by reducing specific power as you can by moving to a higher wind resource bin. The time trend shown here in the upper right is also instructive. There we see average specific power by project vintage, in this case plotted on an inverted scale so that it moves directionally with capacity factor, which is also averaged by project vintage here. And you can see that there is a strong correlation between the two. As average specific power has declined, average capacity factor has increased. And although this reduction in specific power from turbine upscaling does come at a cost, namely the extra cost of the larger rotor, so far the gain in generation has outweighed the incremental upfront cost, enabling both PPA prices and LCOE to decline on the order of 60 to 70% over this same period, as shown in the 2 graphs here on the bottom. So this trend toward lower specific power turbines has clearly been beneficial to date, but the question that we looked into is whether this trend is likely to continue going forward. And so to answer that question, I'm going to turn the mic over to Eric Lantz, who will run through NREL's geospatial analysis of future scaling scenarios. So Eric, have you joined yet?
Hey Mark, I am online.
Awesome.
Can you hear me?
Yeah,
right.
I'm gonna give you control of the slides here.
Okay, excellent.
All right, you should have that. Thanks, Eric. Take it away.
Great, thanks, Mark. Let me just see if I can advance the slides here.
If you might have to click on the slide first to advance it.
Yeah.
There you go.
Uh-oh, did I go to? All right. Yep, I did go to. Sorry about that. Very good. Well, thanks again, Mark. So as Mark was talking about, really what we wanted to do with this portion of the analysis is explore the conditions under which these historical trends that we've seen towards lower specific power will continue or not. And so to do that, we set up a relatively simple set of different turbines with different specific power. Those are shown here in the upper part of the table. We had our 2018 average turbine, which was just the average turbine characteristics for turbines installed in the US in the calendar year 2018. As Mark talked about earlier, that resulted in a specific power of about 230 watts per meter squared. Then we scaled that turbine up to the 5 megawatt class. And we wanted to have one turbine that was relatively analogous to our 2018 average in terms of specific power. That's our 5 megawatt, 230 watt per meter constant specific power turbine that's shown there. We also had our low specific power or low SP turbine, which Mark talked about a little bit earlier. It targets that 150 watt per meter squared level, which sort of represents a continuation of the historical trends that we've seen. And then to kind of keep things at least somewhat symmetrical, we included a high specific or high SP turbine, which has a specific power of 270 watts per meter squared, certainly higher than our 2018 average, but relatively consistent with what we're seeing in terms of commercial offerings in the 4 megawatt class today. With those 3 turbines in hand, we wanted to kind of at least keep some of the variables constant. So you can see our hub heights there for those 5 megawatt machines are all 140 meters. And then we applied a set of Capex scenarios to those turbines, which we'll get more into a little bit further along here. But for the sake of just kind of setting the stage here, we had those 3 Capex scenarios, again, shown on here on the lower portion of the slide. The favor low SP scenario, where actually we have a constant Capex of $1,500 per kilowatt for all 3 turbine options. Our reference scenario, which falls sort of in the middle here, reflects both some empirical and modeled estimations of what the price spread might be between lower and higher specific powers, again, as a function of the larger rotor sizes for the lower specific power. And then our third scenario was our favor high SP scenario, where we took those historical market spreads in pricing between lower and higher specific power, and we exaggerated them. In this case, it was basically plus or minus 16% relative to the constant SP turbine, and that was a double the amount of the spread that we have in the reference scenario, which was a plus or minus 8% in Capex. Let's see here. Don't want to advance too many slides at once. There we go. So with those turbines in hand, we actually then, to make this geospatial in nature, we applied those turbines to every geospatial pixel for wind resource data that we have in the US. Those results in terms of net capacity factor are shown on this slide. Starting at the top, you can see the capacity factor results again across the whole contiguous US for our 2018 average turbine. Then as you go down in terms of the boxes here, you can see the constant SP turbine. It has a similar specific power, but it's up at 140 meter hub height as opposed to the 88 meter hub height that we used for the 2018 average. And so you can see that the distribution there does shift to the right. The median is shifted actually 7 percentage points, and that's the result of the hub height change. The next sort of purple box down shows the results for the low SP turbine. This one obviously shows the difference of the change in hub height, and then also the difference between that 230 watt per meter squared and 150 watt per meter squared capacity factor, or specific power, and that gives you another 7 percentage point change in terms of the median capacity factor. I should note there, actually, the dashed lines, if you can't see it in the legend on the figure, those dashed lines represent the 25th and 75th percentiles within the distributions, and the solid black lines represent the median values. The high SP turbine, the bottom orange color distribution, there you have obviously the bump up from going from 88 to 140 meter hub heights, but you also have a slightly higher specific power, in this case of 270 watts per meter squared. So you see the distribution shifted slightly to the right, but not as much so as that constant SP turbine. So those are your capacity factor results. When we take that and apply a Capex in order to compute LCOE, we can show the same types of distributions on an LCOE basis. In this particular slide that you're looking at the moment, it reflects our favor low SP scenario, where you have the constant or equivalent Capex across all 3 turbines. And here you can see that the cheapest sites are obviously, not surprisingly, related to the low SP turbine technology. And you get many sites that are actually below the $40 per megawatt hour threshold. For the constant and high SP turbines, the bulk of the distribution there is sort of closer to the $40 to $60 per megawatt hour level. These are relatively intuitive results when we're thinking about applying an equivalent Capex across all 3 of the turbine types. Just trying to get the slide to advance here to the next one. Great. Okay, so we talked about the 3 different cost scenarios, Capex scenarios that we used. Sorry about that. All right, struggling with the lag here just a little bit.
How about if I just go ahead and advance them for you?
Yeah, that'd be great, Mark. Thank you.
So I think this is the one you want. I think it's up right now.
That's right. That's indeed. Slide 13 here. And so what we're showing here, obviously, is the results from our 3 different Capex scenarios. On the top, you have the favor low SP scenario, which is the same data that we were looking at on the prior slide, but we're focused on just the differences in LCOE for each specific site relative to the constant SP turbine. So you can see that, for example, in the favor low SP scenario, your constant or your high SP technology is somewhat more expensive than the constant, which would be the 0 value, and then the low SP technology is relatively cheaper as compared to the constant. Obviously, it also comes in cheaper than the high SP turbine technology. When we focus down on the reference scenario results, you can actually see that the low SP results are still, in virtually all cases, lower in cost than the constant SP and the high SP turbines on an LCOE basis. But you do see a little bit of narrowing in terms of the cost difference between the high SP turbine and the constant SP turbine. For the favor high SP scenario, this is really the only one where you see the high SP turbine technology start to become relevant. It certainly doesn't necessarily always come out or show up as the cheapest turbine technology. In fact, the low SP turbine technology beats it out in many cases. but you do see substantial overlap there between the low SP and high SP turbines. The upshot here is that basically under the conditions that we've modeled, and when you apply them across all the pixels in the contiguous US, the low SP technology looks really quite competitive. Do you want to advance to the next slide, Mark? Yeah, so we took those same results that we were looking at previously in sort of distribution form and went ahead and mapped these to add a spatial dimension. There's two specific Capex scenarios represented here, our reference scenario and our favor high SP scenario. In the reference scenario on the left, you can obviously see that the low SP technology wins out in virtually every site, whereas the favor high SP scenario on the right, it's really the highest wind resource regions where the high SP turbine is indicated to be relatively viable. So the takeaway from the LCOE-based analysis here is that essentially, if there's a need or value to expand the geographic footprint of the wind industry, then the historical trends that we've seen towards lower specific power could well be expected to continue in the years to come. On the other hand, if the wind industry wants to focus on the very high wind speed sites that are generally correlated with the green shaded areas on the map where the high SP turbine is relatively favorable under the favor high SP scenario conditions, where you have that relatively larger spread in cost or greater penalty to go to larger rotor sizes, then you can see that you could, or at least it's plausible that perhaps that trend towards lower specific power might slow or possibly plateau in the years to come, again, depending on that actual cost spread in turbine technology and the focus of the industry in more high versus medium wind speed sites. So those are the results of our LCOE analysis and the application of that across the whole contiguous US. Obviously, though, LCOE, as Mark mentioned up front, is only one portion of the story here. It's also useful to look at things from the perspective of value. So Mark, I don't know if you want to push it along to the next slide. And with that, I can turn it over to Dev Milstein, who will talk us through the market value implications.
Hi, everyone. It's Dev, and I'm excited to talk about market value implications here. So this is an analysis based on historical prices in 2018, so it's retrospective, but recent in focus. Okay, so if we look on the left side of the slide here, we see we can break costs and market value into different components, and we're always looking for a balance between costs and value. On the value side, we're focusing in this work on the capacity value and the wholesale energy value. The capacity value is based on capacity rules that are set up in each of the different independent system operator regions. And energy value is based on wholesale energy prices in general. We focus on those two values rather than ancillary services because we think those are sort of the larger value portions in this case. If we look below that market value and cost balance there, we can see one of the motivations for focusing on this market value, and this is that as wind increases its market share, we expect to see value decline over time. This is demonstrated in that figure there, which shows quite significant relative decline in the value of wind as market share increases to pretty substantial portions. Now, we've done some general work on market value of wind across the US. And here, again, on these two figures to the right, we're focusing on 2018. And we can see that the value of wind varies quite a bit by region, with ISO New England and CAISO having the highest value for their wind projects, and SPP and ERCOT having the lowest value for their wind projects. Part of that is just due to different sources, factors outside the control of the wind industry, but also part of that is due to high penetration of wind in SPP and ERCOT. Below that regional bar graph, we can see a map of all the existing wind projects in 2018, and we've estimated the value, energy and capacity value of each of those projects. And we can see the same regional variation, but also in some cases, variation within a region. For example, we can see in New England, lower prices up north and higher prices near the major population centers. Or sorry, higher values near the major population centers. Okay, so how do taller, lower specific power turbines actually increase the market value? And the main mechanism through which they increase market value is by operating at rated capacity more often and operating at lower wind speeds at higher capacity. And so what that does is spread the generation for a low specific power turbine across many more hours of the year rather than just being focused at the windiest hours of the year. That's specifically valuable in regions with high wind penetration, as the windiest hours will tend to have lower prices as the supply of wind power is greater during those hours, and with high penetration, that can lower wholesale energy prices. So with low specific power turbine, you're able to generate more outside of those hours during higher price hours in general, and that increases your average value. There's a couple other mechanisms through which value increases we'll talk about later. But specifically, by spreading out your generation over more hours, you're able to make better utilization of transmission equipment. And you can reduce your forecast error as you lower your overall variability of wind power by spreading it out in that manner. So how much of a difference does low specific power make to the amount of time turbines run at rated capacity? And that's sort of the question that we answer in this figure to the right. This is not a comprehensive analysis. It's just we picked 4 existing wind project sites in Texas, and we looked at how the number of hours operating at rated capacity changed by changing turbine type, and also by increasing hub height. So here we go from the 2009 average turbine up to 2018 average turbine. We see rated capacity doubles from roughly 10 to roughly 20, sort of order of magnitude there. And so the number of hours it's operating at rated capacity doubles in that situation. And then if we go up to our low specific turbine, which is again at a higher hub height, 140 meters with a specific power of 150 watts per meter squared. And that again doubles or even more than that, the number of hours it's operating at rated capacity to 40% or above. So it's a very large increase to the time turbines operating at rated capacity, which allows for the value increases that we're going to show. Okay.
Dev, should I just advance the slide?
Yeah, I think the lag
okay.
is too hard to control here.
So there you go. It's on 18 now.
Okay, great. Okay, just to talk about the methods for a minute, we're looking at energy value and capacity value based on 2018 prices and the rules for capacity value set up by each ISO in 2018. So this depends on, for every existing site, we match the site to a local node for the wholesale price series. There's over 50,000 local pricing nodes in the country, and so we're able to get a close match at most sites within a few kilometers, really. And this allows us to get local pricing series at each node from 2018 by the hour. And then we also developed hourly wind generation profiles and wind speed profiles at each site using a combination of model data and recorded generation. I won't go into the details of how we debiased that model data, but we spent a lot of effort doing that and have developed debiased wind speeds at each hour and different hub heights at all these sites. So we can use those wind speeds to model generation of our different turbines and match that generation with the hourly price series at each site individually, and that allows us to develop estimates of the hourly energy wholesale value. We can also use those hourly profiles of generation to match with the capacity rules and capacity prices in each independent system operator region and develop capacity value estimates. We analyzed these same 2018 average and low SP turbine configurations that have been mentioned a number of times. We're also looking at comparisons to the 2009 average turbine. And again, just the caveat, these are retrospective analyses, so it won't necessarily show what will happen in the future, but we think there's a lot of insight to be gained by looking at this, especially given the different levels of market penetration in the different regions. Okay, next slide, Mark. Okay, so to jump into the results here, on the top half of this table, we have the different turbine configurations. And then on the bottom, we have the effect on value. And so we compare the 2009 average to 2018 average and the low SP turbine to the 2018 average. So the 2009 average turbine had a lower total value of about 41 cents per megawatt hour compared to the 2018 turbine. So as turbines had lower specific power in 2018, that increased their market value on a national average by 41 cents per megawatt hour. But we see that much more gain is possible going to the low SP turbine up to $1.40 per megawatt hour. Most of the future gain in value comes from the energy value rather than the capacity value. And then one thing that's not shown here is that most of that value also comes from the switch to even lower SP rather than the higher hub height. When we just increase the hub height, we only get a small value increase, but then when we go to the low SP turbine, we get the 2 to 3 times greater increase in value. Okay, next slide. So looking at the individual projects, which were the input into those national results we just showed, we can see that the highest value projects, which are the darker blues here, are found in the regions with highest wind penetration, like ERCOT and SPP. We also see some variation within regions. If you look at ISO New England, we see a high value in the north of ISO New England and lower value in the south of ISO New England. And so this again is the delta. This is the increase in value you get from moving from the 2018 average turbine to the low SP turbine. Okay, next slide. Okay, so this is the same results, but looked at with in a different manner using histograms here, so you can actually see the value numbers more easily. We can see here that ERCOT and SPP have the center of their distribution of value increased due to moving to the low SP turbines of $2 to $3 per megawatt hour. Other regions, MISO and New York ISO, have lower increases to value, and then areas like CAISO and PJM are pretty neutral on average in terms of the change in value. And we can see this big spread that we saw on the map as well for ISO New England in terms of the value. Next slide. On a percentage basis, we can see that in SPP and ERCOT, that $2 to $3 increase in value we saw is about 10 to 15% increase in the market value in a relative sense. And in the rest of the regions, we see a lower increase to market value due to the low SP turbines. Part of that is just because wholesale prices are lower in ERCOT and SPP, and then also part of that is because the penetration of wind is higher in ERCOT and SPP. Okay, next slide. And then here, this shows graphically how much higher the wind penetration is in ERCOT and SPP, plotted versus the percentage increase in value we see from the low SP turbines. And so we see this much higher percentage increase value for ERCOT and SPP from the low SP turbines than all the other regions. And the other regions, the increase in wind penetration from 0 to 10% does not seem to be correlated much with the percent increase in value for the low SP turbines. It's not till you get to this higher wind penetration that you see a jump in the value of the low SP turbines. Okay, and then another detail about this value change on the regional level is that the orange bars here show the energy value change, and the gray bars show the capacity value change. Now, we mentioned on a national level that the energy value dominates. You can see that all the way on the left here, with the orange bar leading to the most of the increase in value for the low SP turbines. And but in certain regions, we actually see capacity value be quite important, such as ISO New England, and it's smaller than energy, but still important in SPP. ERCOT, of course, doesn't have a capacity market, so we see no value increase from capacity there. CAISO's in a sort of unique case where the, well, we don't need to get into the CAISO detail unless there's a question on that specifically. But the main takeaway is that in most regions, the energy value is dominant here. Okay. Last slide. So just a couple key takeaways. Between 2009 and 2018, the value of turbines has increased due to the reduction to specific power over that time. But much more progress is possible on that front, looking at the modeled low SP turbine. The value enhancement is greatest with high wind penetrations, especially once you get up to that, close to that 20% level. Is also great, larger in regions with transmission constraints, like the northern part of ISO New England. Value enhancement was dominated by energy rather than capacity value, and the reduction in specific power had a larger impact than the increase in hub height. All right, and now I will pass the controls back to Mark to talk about additional benefits of taller, low specific power turbines.
Okay, thanks, Dev. So I am going to quickly finish up by touching on 3 additional incremental benefits of low specific power turbines that we identified and also were able to evaluate, namely greater transmission line utilization, leading to lower transmission costs, lower balancing or ancillary service costs, and then also improved financing terms. So for transmission, the simple fact that the low SP turbine has a greater capacity factor means that one can spread out the relatively fixed transmission costs associated with building spur lines or implementing required grid upgrades. You can spread those fixed costs across more megawatt hours, leading to a lower dollar per megawatt hour transmission expenditure. And based on some reference or benchmark data for transmission costs, we estimate that the low SP turbine would save about $1.60 per megawatt hour relative to the 2018 average turbine. Now, only about a quarter of that, just the portion corresponding to spur lines and direct interconnection costs, accrues to the project owner, and the rest of it, which is really the majority of it, is socialized across the entire grid system. For balancing costs, we once again find that the increase in megawatt hours from a higher capacity factor outweighs the incremental reserve requirements imposed by the low SP turbine, leading to a slight reduction in balancing costs. We estimate it to be somewhere in the order of $0.2 per megawatt hour, and in this case, all of that is socialized. And given the time, I'm not going to get into the methodology and assumptions here, but you're obviously free to look at those a little bit later. Finally, the fact that the low SP turbine spends more time at rated capacity means that its output is less variable from year to year, as shown here in the graph in the lower right. If lenders acknowledge this reduction in interannual variability by allowing a lower debt service coverage ratio, then that would enable projects to take on and support a greater amount of debt. And because debt is typically cheaper than equity, this should reduce overall financing costs. Based on some runs of our financial models, this benefit could reduce LCOE by approximately $0.3 per megawatt hour. So in aggregate, these three additional benefits amount to roughly $2 per megawatt hour, and more than half of that is socialized rather than accruing directly to the project owner. Again, these benefits are above and beyond the LCOE and market value estimates that we presented earlier. Okay, just to quickly wrap up, the significant turbine scaling that we've seen over the past decade has already provided both LCOE and market value benefits in the US, but there's clearly more to be gained from a continuation of this trend. Our analysis that we ran through here today suggests that moving to 150 watts per square meter could potentially result in a $6 per megawatt hour lower LCOE, a $1 to $3 per megawatt hour boost in market value, and then another $2 per megawatt hour or so in savings from lower transmission, integration, and financing costs. So in total, this sums to roughly $10 per megawatt hour, which may not sound like all that much, but considering that wind PPA prices are at or below $20 per megawatt hour in many parts of the country, it really is a significant impact, representing savings somewhere in the order of around 50%. So with that, thanks for sticking with us and for submitting some questions here, which we will now turn to. So let me pull those up. The first question that came in, someone asked whether specific power levels are similar for offshore wind turbines as they are for land-based turbines. And I guess I can take a first stab at that, but Dev and Eric can jump in as well. And the answer there is generally no, and that's because a big part of the expense of building offshore is the foundation. So you really want to put as much capacity as you can on each individual foundation. For example, the latest round of offshore turbines are up in the 12 megawatt range compared to maybe 4 to 5 onshore. And so to get down to a low specific power level on a 12 megawatt turbine would just require a really large blade. One example of that is, I think the GE 12 megawatt turbine, the blade on that I think is slightly over 100 meters. And that's roughly the same size blade that would go on the low SP turbine that we've been talking about, which is only a 5 megawatt turbine. So you can see that there's quite a difference there, simply because the offshore wind capacity, the rated capacity is much larger. Okay, the next question, someone asked about the capacity factor distributions that Eric showed, so maybe I'll throw this one to him. He's wondering why all of the distributions of the various scenarios seem to have kind of bimodal distributions, or two different camel humps, that kind of thing. Eric, can you address that?
Yeah, sure. Thanks, Mark. So, I mean, I guess I'll try and give you an answer here. It's essentially simply just the representation of the turbine power curves and the variation in the wind resource that you see. So there's no, grand statistical explanation, at least that we've been able to discern as of yet, but it's really just that simple relationship between, what's the wind speed at a given site and how does the power curve interact with that to influence the capacity factors. Obviously, in this case, it just so happens that when you move to that higher hub height, you can see that sort of that camel shape is a little bit more exaggerated. And then it's even more exaggerated with the relatively lower specific power turbines, both the low SP and the constant SP. But that's just a reflection of how the capacity factors are changed as a result of that higher hub height and different power curve.
Okay, thanks, Eric. Here's another one. Well, for either one of you, really, someone's asking if there are any adverse impacts associated with higher hub heights, for example, environmental impacts or air transportation, I guess, meaning, commercial aviation. Anyone want to take a stab at that?
Sure, I can take a quick stab at that. I'm not sure that I would use the word adverse impacts, but there are certainly things that change as you go to higher hub heights. As you note, I think that there is greater concern with respect to aviation. As you move higher and higher above the surface, you start to move closer and closer to the realm in which you need sufficient radar coverage and or, depending on how high you are and how near you are to a particular airport, you might start impacting flight routes and utilization of airspace by aviation. So that's definitely a concern that needs to be considered. The other one that most often comes up is that you can see the turbines from farther away. So as they penetrate, further into again above the surface level, their visibility increases with line of sight distance. On the flip side of that one, though, is that if you move towards at least larger turbines, you may have fewer of them, so they'll be more visible from further away, but there will be fewer of them on the landscape. So that one's kind of a double-edged sword.
Okay, thanks, Eric. Dev, here's one for you. Someone was asking about, I think, the slide where you showed the percentage of time that each of these turbines was operating at rated capacity, and the question is the increase in operating hours due to pushing the lower boundary of the minimum operating wind speed, or is it more a case of operating in more of the low wind speed hours?
Yeah, so that specific figure just looked at the number of hours turbine operated at rated capacity. So that specific issue is from shifting that point where a turbine operates at rated capacity down the wind speed curve. So maybe the low specific power curve operates at 100% of its rated capacity, starting at 8 meters per second instead of 12 meters per second, or some number like that. And then that change in that limit then increases the total number of hours it operates at rated capacity. But there's a secondary effect that sort of hints at, which is that it's also at wind speeds below that sort of rated capacity point, it's all operating at a higher capacity factor, even in those other wind speeds as well.
Yeah, so thanks, Devin. I guess I would maybe just add to that if you take that one step further and look at the value impacts, it's also important, what the wholesale prices are doing in any of those given hours, and the value boost really comes from a greater proportion of the wind generation occurring during low wind speed hours when, at least in some markets, wholesale prices tend to be higher because there's less wind in general or in total flowing onto the system. Okay, we had a question about, well, really sort of two questions that sort of touch on this. The fact that we're kind of looking at wind in isolation here, but obviously there's solar coming onto the grid as well. And people are kind of wondering about not only the value, the projected value decline of renewables or of wind as penetration increases, and how that might change if you think about it from both wind and solar as opposed to just wind penetration increasing. and also whether this the same value increase that we've shown here, whether we'd expect that to continue if you get more solar on the grid as opposed to more wind. Do either of you guys want to take a first cut at that?
I could talk about that.
Great.
So a very basic rule of thumb is that you know, wind peaks in the nighttime and solar peaks in the day. But beyond that, just in terms of correlation for any specific hour, wind plants will be more correlated with other wind plants than solar plants. And so I think that the results we presented here in terms of value increase are going to be most sensitive to other wind plants coming online, and specifically other low specific power wind plants coming online. They'll be more sensitive to that than to solar coming online. There'll be some sensitivity to solar, but much more to other low specific power plants. We presented marginal results based on unchanging, or just based on the exact wholesale price series as we saw it. And so things that will reduce wholesale prices in the future might be other low marginal cost energy sources like solar or wind, but what these results will be most sensitive to is other low specific wind power turbines as opposed to solar.
Yeah, and I guess I would just add to that we do see in some markets that a higher penetration of solar, may actually increase the value of wind. And I think California is a good example of that, where you've got so much solar coming onto the system midday, it's pushing the net load or the net peak load into the afternoon and evening hours when the wind typically ramps up. So these two resources, can certainly interact with respect to this question of market value. Let's see, we got a bunch coming in here, so this is good, but it's a little hard to keep up with them. Someone's asking about wake losses. Would the level of wake losses be different between low and high specific power turbines?
I guess I can take a crack at that one, Mark. This is Eric. I think the answer is that it depends. I think, the wake losses are a function of a variety of factors that are both site-specific and turbine-specific. So I guess I would hesitate to say that there is, a specific rule of thumb that really applies here. However, oftentimes sort of just classically, when wind plants are designed, they are spaced relative to the prevailing wind direction by distance of rotor diameter. So what you would typically see would be slightly greater spacing with lower specific power turbines relative to higher specific power turbines in order to sort of better manage that wake. So I guess you could say that the wake effects are somewhat larger for larger rotor machines, not necessarily lower specific power, but at least larger rotor machines, but that is still able to be managed either with turbine spacing or potentially advanced controls.
Great, thank you. Here's another one. Someone's wondering about the reasonableness of our Capex assumptions for the low SP turbines, given that the blades are basically 100 meters long. And that would imply that these longer blades might impose significant costs on other turbine components like the drivetrain and the towers, et cetera. So I think kind of implicit in this question is that the current empirical difference between low SP and high SP that we see in the market, may not really apply going forward, given just the sheer size of the blades. And I guess one area where that particularly becomes the case is in terms of just transporting these things to the project site. As part of this overall Department of Energy initiative that funded this work, there was a supersized blade study conducted by DNV GL where they looked at some of the logistical, manufacturing, and transportation related constraints associated with these very large blades required to hit this 150 watts per square meter target. So I guess I would encourage you to take a look at that. If you Google supersized blade, I think it'll be probably the first thing that shows up there. But just wondering, I guess, maybe, I don't know, Eric, if you have any thoughts on this about how reasonable the Capex assumptions are, given that we're talking about 100 meter blades here.
Yeah, I think it's a very fair question. As I mentioned at the outset of my portion, our analysis was really not intended to be predictive, but rather to explore the conditions under which the historical trends that we're seeing may or may not continue, at least as it applies to low specific power and a trend towards even lower specific power. So I think the question is very well founded. I tend to think that the potential risks for deviating away from that historical pricing spread that was sort of grounded in our reference scenario are really more on the transportation side of things than on the other, foundation or tower impacts, sort of the other turbine systems. The ability to get those blades to site is certainly a non-trivial challenge, at least in a land-based environment. But there are other system impacts. So I guess really the answer is we'll see. But again, our results are sort of based on obviously the assumptions that hopefully we were transparent about showing. And so you can see that if those CapEx values do come to fruition and the pricing spread does stay consistent with the historical sort of spread that we've seen, then we can be bullish about low specific power. If on the other hand, we aren't able to solve the transportation challenges in a cost-effective way, then you won't be able to capture those lower LCOE benefits, and you may end up with higher LCOE or need to pursue other innovation opportunities.
Okay, thanks, Eric. And just one last question, because we are at the top of the hour. Someone asked what R&D is needed to achieve wind systems with lower SP rates. And maybe I'll just take a quick crack at that. This work was funded by the Department of Energy under an initiative called the Big Adaptive Rotor Initiative. And really the whole point of this project is to come up with turbine designs that can kind of get us towards or move us towards this 150 watt per square meter target. And so there are engineers at NREL and Sandia who are working on, and Oak Ridge, who are working on a variety of R&D projects really aimed towards getting us towards that goal. And just a few of the different turbine designs they're looking at, I mean, they're exploring kind of slender, flexible blades, which would enable us to maybe bypass some of the binding transportation constraints. If you can kind of bend the blades a little bit as you're going around rail curves, for instance, you can then use longer blades on your projects. They're also looking at the possibility of a downwind turbine configuration, which really lends itself more readily to very large rotors. So there is a lot of good work currently happening within the DOE ecosystem on this question of R&D needed to achieve lower specific power. So with that, we are now a few minutes past. So thanks everyone for attending. Thank you to Deb and Eric for participating. And there are still some outstanding questions here that we will try to follow up with you via email if we have your address. So thanks everyone, and have a great afternoon.